Hi, welcome to this video on AQA P2 covering mechanics and radioactivity section of the course. We start with resultant forces. So the first thing you need to know is when objects interact, they exert an equal and opposite force on each other. So say I hit the wall with 5 newtons, that means the wall is also going to exert a force on my hand of 5 newtons. The resultant force is the sum of all the forces acting on a single object. So in this first example, we've got a 5 newton and a 4 newton force acting in the same direction, so we add the two forces together to get a resultant force of 9 newtons to the right. In this second example, our forces are acting in opposite directions, so we need to subtract them, so we do 10 minus 5, which gives us a resultant force of 5 newtons, and that will be to the left. So why is resultant force important? Well, it's important because it tells us how the motion of an object is going to change. If there is zero resultant force, there's no change in the motion. So if we had a stationary object, it would stay stationary. Whereas if we have a non-zero force acting on a stationary object, it's going to start moving. It's going to accelerate in the direction of the force. By contrast, if we have an object that's already moving, then it's going to, if there is zero resultant force, it is going to stay moving at exactly the same speed. It doesn't need a force to keep moving, okay? So a zero resultant force, it stays at a constant speed. If we have a non-zero resultant force, then it's either going to accelerate or decelerate depending on whether the force is in the same direction as the motion or in the opposite direction. If we look at a distance time graph, we can see how we can calculate speed from that. We know that speed is distance divided by time, and speed is measured in meters per second, and distance in meters and time in seconds. If your data gives you any other thing, so like on this graph it's given you time in minutes, you need to convert that into the correct unit, so it needs to be converted into seconds in this case. The gradient, or the steepness of the graph, is going to tell you the speed. So in the first section of this graph, we're going at a slow speed, it's got a low gradient, and in the next section it's going faster. If it's horizontal, that means the gradient is equal to 0, and it's a stationary object, it's not moving at all. You need to know the difference between speed and velocity. Velocity is the speed something is travelling in a particular direction. So that means if you go somewhere and then come back again, your overall velocity has been 0 because you've not moved anywhere from that point. Whereas your speed may have been constant throughout. We can use a velocity time graph to show how velocity changes over a journey, and the gradient of that gives us the acceleration. So acceleration is measured in meters per second squared, and that's equal to the change in velocity divided by the time taken for that change. The steeper the line on the graph, the greater the acceleration. So section C on this graph has a higher acceleration than section A does. Section B isn't accelerating at all, it's at a constant velocity. Be careful that you don't say that it's stationary. We know it's not stationary because it's got a velocity of 40 meters per second throughout. The other thing we can calculate from these graphs is the area under the graph, which gives us the total distance travelled. So we break down the graph into triangles and rectangles, calculate the area of each. So a triangle would be half base times height and a rectangle just base times height. Add them together to get the total area under the graph, and that will tell us what the total distance travelled is. Okay, if your velocity time graph is going downhill, then that shows a deceleration because it's getting slower. You need to know how forces are involved in the braking process. So when braking, we have friction, which reduces the kinetic energy of the vehicle. That kinetic energy is converted into thermal energy, so the temperature of the brakes and the surroundings increases. The thinking distance is the distance that you travel during the driver's reaction time. The braking distance is the distance travelled between pressing the brake and coming to a complete stop. And the total stopping distance is those two added together. So stopping distance is thinking distance plus braking distance. You do not get given that equation, you need to know it. What you also need to know is some factors that affect thinking distance and braking distance. Affecting both is speed. If you're going faster, then you're going to travel further during that reaction time. So that's how it affects thinking distance. If you are going faster, then you're going to have more kinetic energy. So a bigger energy transfer is needed to stop the car. So your braking distance is going to be longer. Other factors affecting thinking distance are any factors that are going to affect the reaction time. So things like age, drugs, alcohol consumption, tiredness, distractions. Other factors that might affect the braking distance are anything that could affect the friction between the brakes and the wheel, or between the wheel and the road. So the quality of the brakes, the quality of tyres, the type of surface that the vehicle is driving on, and the road and the weather conditions, for example, if it's icy or wet. Another thing that will make a difference is the mass of the car, because the bigger the mass of the car, the higher the kinetic energy is going to be again. So that's going to mean that there's more energy that needs to be converted into heat, so it's going to take longer for that process to happen. Terminal velocity, this is the bit where we get to chuck someone out of an aeroplane. So as you get thrown out of the aeroplane, initially you have weight acting downwards and no air resistance at the moment you get pushed from the plane. So that causes you to accelerate downwards. You get faster, and so air resistance increases, because air resistance is the force due to you colliding with the air particles. The faster you're going, the more air particles you're going to collide with every second. So as you continue to accelerate, the air resistance gets bigger and bigger until eventually it is the same size as the weight. When these two forces are the same size, the resultant force becomes zero. If the resultant force is zero, there's no longer any acceleration, which means there's a constant velocity. We call that constant velocity terminal velocity. They might ask you about this similarly in vehicles, why they have a top speed. It's the same thing. As the speed builds up, the air resistance builds up. Air resistance builds up until it's the same as the forward force. Resultant force becomes zero. Acceleration stops. There's no more acceleration. And we're at terminal velocity. Now, if you're the person falling out of the plane at this point and you've got to terminal velocity, that terminal velocity is going to be so high that it's going to kill you on impact with the ground. So you're going to hope that you've got a parachute on. By opening a parachute, what you're doing is you're increasing the surface area. So if you're increasing the surface area, you're going to have more collisions with air particles every second, so your air resistance is going to rapidly increase. That means the resultant force is going to be acting upwards, which gives you a deceleration overall. As you slow down, the air resistance gets smaller again because you're hitting less air particles per second, and eventually that balances out with your weight again, and you reach terminal velocity again, but this time the terminal velocity is a lower speed. You need to know that weight and mass are not the same thing. Weight is a type of force that is due to gravity. Weight is measured in newtons, mass is measured in kilograms. Okay, so the gravitational field strength on Earth that you need to use is 10 meters per second squared, or 10 newtons per kilogram, and you times that by the mass to get the weight. Okay, we measure weight with a spring balance. Forces can also be used to change the shape of objects. For example, if we stretch a spring, then we do work on that spring, which is converted to elastic potential energy, which is a type of stored energy. What Hooke's law tells us is that the amount of extension of the spring is directly proportional to the force applied, provided that we don't reach this thing called the limit of proportionality. So what we mean by directly proportional is that if one thing doubles, the other thing also doubles. You'd see that on a graph as a straight line going through the origin. To calculate the work done when a force is applied to an object, you need to do the force times the distance. Work done is an energy, it's amount of energy transferred, so it's measured in joules, force in newtons and distance in meters. Power is the rate of transfer of energy, so how much energy is transferred per second. Energy measured in joule, powers in watts, and time needs to be measured in seconds. Two other types of energy that you need to be able to do calculations with. Gravitational potential energy, again an energy, so measured in joules, is equal to the mass in kilograms times gravitational field strength, which we already said is 10 on Earth, times the height in meters. Kinetic energy is half times the mass times the velocity squared. Don't forget to square the velocity. It's where most people end up missing out a mark on an energy calculation question. Okay, you square just the velocity as well, not the mass times the velocity. Now, the other thing that's really important with these energy questions is that they often use the principle of conservation of energy, which you looked at in P1. That says that energy is neither created or destroyed, it can only be transferred from one form to another. So if, for example, you're looking at a circumstance with a roller coaster, the amount of energy it has at the top of the hill is the maximum amount of energy it can have when it reaches the bottom. That gravitational potential energy would be converted into kinetic. So they would ask you to calculate the GPE it's got and then give you, for 1 mark, what is the maximum kinetic energy. You just give the same value. Momentum is the mass times the velocity of an object. It is a measure of how easy or hard it is to stop an object. They quite often ask you to give the units of momentum. It's kilograms meters per second. Just multiply the kilograms times the meters per second if you forget. Now, the principle of conservation of momentum tells us that in a closed system, the total momentum before an event is equal to the total momentum after the event. So what that means is, say for example a collision or an explosion, the total momentum before, if you calculate the total momentum of the objects before they collide or explode, that's going to be equal to what the total is afterwards. You will be given enough of these things that you can work out the rest. What they quite often like to do is they quite often like to give you an initially stationary situation, for example firing a gun or 2 skaters about to push apart, that kind of thing, where the initial momentum is 0, in which case the forward momentum of one thing has got to be equal to the backward momentum of the other. So when you're looking at these types of questions, start by working out the total momentum before the event happens. Then you're going to say that that's equal to the total momentum afterwards. You often get a mark for saying momentum before equals momentum after. And then finally, you're going to use all the information you've been given. So you'll have some masses and velocities, and you'll need to work out what the missing value is. That's only likely to come up on a higher paper. Okay, so moving on to radioactivity, you need to know the structure of an atom. So we've got a central nucleus that contains neutral particles called neutrons and positively charged particles called protons. Around the outside of that, there are electrons which are housed in shells. You need to know 2 key definitions here. Ions are atoms that have gained or lost electrons, and isotopes are elements with the same number of protons and different numbers of neutrons. Memorize those definitions. The atomic number is the smaller number on the periodic table. That tells us how many protons there are. The mass number is the bigger number, which is the number of protons plus neutrons added together. So if you want to work out the number of neutrons, you do the big number minus the small number. For the number of electrons, it's usually the same as the number of protons unless it's charged. Okay, you need to know the 3 types of radiation, alpha, beta and gamma. So alpha radiation is made up of 2 protons and 2 neutrons. It's a helium nucleus. It has no electrons. It can be stopped by skin and paper, and it can travel up to 10 centimeters in air. And the reason for that is because it's very strongly ionizing, so it interacts very easily with other particles. Beta is a high-speed electron that is ejected from the nucleus. Often confuses people. The electron is created by the nucleus and spat out. It can pass through skin and paper, but it is stopped by thin aluminium. It has a range in air of about 1 meter, and it is fairly weakly ionizing. Gamma is an electromagnetic wave. It's part of the electromagnetic spectrum that you studied in P1. It has much higher penetration. It is stopped by very thick concrete or thick lead. It can travel for several kilometers in air. In fact, it doesn't ever go away completely, but the energy reduces, and it's very weakly ionizing. Background radiation is the radiation that we're constantly being exposed to. Natural sources include food and drink, radon gas, rocks and building materials, and cosmic rays. Human or artificial sources are nuclear power, nuclear weapons, and medical sources, for example, medical tracers. Okay, if you're doing higher tier, you'll need to know how to balance nuclear equations. So the first thing to know is they will give you most of the information, but you have to make the mass numbers add up on either side of the equation, and you have to make the atomic numbers, the proton numbers, add up on either side of the equation. And in order to do that, you're going to have to remember what the mass numbers and proton numbers are for an alpha particle and a beta particle. So here we've got americium-241, which decays via alpha decay. And alpha, remember, is 2 protons, 2 neutrons, so it has a proton number of 2 and a mass number of 4. So to make this balance, we need to do 241 minus 4 to give us 237 for the mass number, and 95 minus 2 gives us 93 for the proton number. Carbon-14 decays via beta emission. Now, a beta particle is an electron, but the process of making a beta particle involves taking a neutron and turning it into a proton and an electron, and the electron is ejected at high speed. So the beta particle has a mass of 0 and a proton number of -1. So we make that balance. 14 equals 14 plus 0. 6 equals 7 plus -1. Okay, so you just need to remember that a beta is 0 minus 1 and alpha is 4, 2. You need to know what happens to these particles in electric and magnetic fields. In both types of fields, gamma goes straight through, and the alpha is deflected to one side, the beta is deflected the other way. Beta is always deflected more because it has a lower mass, and you need to know in electric fields, because alpha is positive, it goes to the negative terminal, beta is being negative, so it goes to the positive terminal. Definition of half-life is it is the time taken for half of the radioactive nuclei in the sample to decay, or for the activity to decay by half. So to work out the half-life from a graph, you find the maximum, half it, draw a line across and down, and circle the time that you come up with, and that will give you the half-life. To check on it, you can half it again, go down, and the difference there will again be 1 half-life. So in every half-life, in this case 2 days, in every half-life, the amount of radioactivity decreases by a half. You need to know some uses of radiation. The most common ones are the smoke detector, thickness monitoring, and medical tracers. The smoke detector uses the americium that we were talking about earlier, which is an alpha emitter. And that means it's highly ionizing, which is really useful for us. It's also low penetration, so the radioactivity only stays within the smoke detector. It can't escape from there, which is also helpful. So we have a little electric circuit set up, and we've got an alpha source on one side of it. What happens is that the alpha source goes into the chamber and ionizes the air, and that enables a current to flow in the circuit. If smoke gets in, the air no longer gets ionized, so the circuit gets broken, and that triggers the alarm. In thickness monitoring, usually we're looking at paper or aluminium production. So what we have is the material going between a set of rollers and a beta source placed on one side of it and a detector on the other. If the thickness of the material increases, less beta can get through, so they move the rollers closer together to make it thinner. If it becomes too thin, then more beta gets through, so that gets detected, and they can pull the rollers apart. They use beta because alpha would be stopped regardless of the thickness, and gamma would get through regardless of the thickness. So the thickness only has an impact on beta. We'd want a long half-life so that the amount of radioactivity coming out of it doesn't change. Medical tracers. Medical tracers use an alpha or beta source injected into your body. Gamma source wouldn't do because it wouldn't be able to be detected outside of the body. The alpha or beta source then is detected outside of the body and can be used to detect problems with the body. So for example, it could be injected in the bloodstream to see whether your kidneys are working properly at filtering out that source. Okay, we want to use a short half-life so that it doesn't stay in your body for long. Thank you for watching and good luck.